Good morning or good afternoon, depending on where you're at. My name is Atarod Azizi Namini. I'm director of the IBT/ABC UTC. Very warm welcome to more than 1,000 sites that have registered to March 2026 monthly webinar. We are very delighted to bring to you a very interesting topic: CDOT, rapid response to hydrogen cracking in grade 100 steel wells at Blue Mesa Reservoir bridges. We are delighted to have with us Natasha Butler, who is a state bridge engineer with Colorado DOT, Keely Matson, department manager with Bridge Division, Michael Baker International, and Francisco Javier, who is a professor at the Purdue University. During the registration process, we have received a number of questions. We're going to try to get to them as time permitted. Couple of things: the deadline to submit abstract is tomorrow, March 20. We hope that to see many of you during the conference, especially if you have enjoyed some of the technology transfer activities that we have had. Thanks to 33 state Department of Transportation that have co-sponsored. Of course, the conference is sponsored by U.S. Department of Transportation through our University Transportation Center. So again, the deadline to submit your abstract online. We are going to provide the PDF copy of all the presentation on our website. You can visit on our website and get all the information, but there's a QR code. But March 20 is the deadline, so please take a note of that. Registration is open. You can go ahead on our website and register. There's a QR code. Travel scholarship. If you know of any, especially county engineers or city engineers or bridge owners that are interested in attending the conference, there's a travel scholarship available. If you are a state DOT engineer, these are all for the US, basically the engineers. So if you are a state DOT engineer, if you're a county, city, and you're interested in attending the conference, it's a very simple process. There's an application. You can go ahead to our website, submit basically your application, and get one of the travel scholarship to attend the conference. This is very important. If you have a bridge engineering project that you feel like it's worthy of getting an award, please, there is an application process and there is a deadline of the June 30. These awards on different categories. We're going to recognize the Innovative Bridge Engineering of the Year award. If you feel like, for example, somebody has contributed to the bridge engineering the most, there's that category. There's an Innovative Bridge Owner Agency of the Year, which is for the states. And then ABC Project of the Year, other innovative bridge technologies in different categories, $10 million, between 10 and 100 and more than 100. So please take a look at that. This is a very great opportunity to recognize the outstanding projects. Also, there is going to be day before the conference, which is November 30. It's going to be for those, this is only for those who register to attend the conference on December 1st and 2nd. We are going to have a full day non-destructive testing workshop that is going to be conducted by very prominent people who are experts in the non-destructive in the industry in the US and Europe. So don't miss this opportunity. There is going to be a lecture portion in the morning and a hands-on demonstration in the afternoon. So take advantage of that. Also, last but not the least, the first US DOT sponsored annual Transportation Infrastructure Summit is going to be conducted in conjunction with the conference. This is a separate event and it is related to all the US DOT activities through the UTC program. This particular event is going to be conducted in conjunction with our conference, and it's a great opportunity for you to see lots of other transportation infrastructure solutions. So please don't miss this. So there is lots of activity going on with this conference, great opportunity. There's also possible opportunity for you to exhibit at the conference. So at this point, I'm going to turn it to Kathy Kroll to share some additional information before we turn it back to our speaker. Kathy?
Thank you, Torad. My name is Kathy Kroll. I'm the co-director of technology transfer for the IBT ABC UTC at FIU. Before we get started with our featured presentation, I'm going to go ahead and share a couple of industry news with you. First, the AISC NSBA's 2026 Steel Conference is coming up quickly. It'll be held April 22nd through the 24th in Atlanta, Georgia. Registration is open. The 4th International Interactive Symposium on UHPC will be held in Des Moines, Iowa, June 14th through the 17th. For anyone interested in UHPC, this is a very valuable conference. Put it on your calendars. Next, the AASHTO Committee on Bridges and Structures annual meeting will be June 28th through July 2nd in Charlotte, North Carolina. Continuing to our own events, our next monthly webinar will be on Tuesday, March 19th from 1 to 2:15 Eastern. The presentation will be exploring the engineering marvels of the Gordie Howe International Bridge. Zaire Youssef, Jonathan Keano from the Windsor-Detroit Bridge Authority, and Kyle Copper, representing Michigan DOT, will be presenting. Mark your calendars for this very interesting presentation. Last announcement, on April 24th, we'll be holding our next quarterly research seminar from 1 to 2:15 Eastern. The featured presentation will be a comprehensive formulation prioritizing bridge interventions subject to flood hazard. Our colleagues from FAMU FSU will be presenting. Registration is open. Sign up now. That's all for our announcements. On to our standard housekeeping items. As many of you may know, these webinars are recorded and posted on the IBT ABC UTC website in the section titled Monthly Webinar Archives. So you can access this and all previous webinars for future learning and to share with interested colleagues. I'd also like to point out that a PDF version of today's presentation is provided. You can download these PDFs during the training session. They will also be posted in the archives. I mention this one more time because sometimes we experience latency issues. So if you're having the speaking and the video aren't aligned, please download the presentation and follow along in real time. But lastly, this presentation will be followed by a question and answer session. We have a number of great questions that were submitted with registration. With that, we'll begin our featured presentation. We are happy to welcome Natasha Butler, the Colorado State Bridge Engineer, Keely Matson, Bridge Department Manager for Michael Baker International, and Francisco Bonachera, a professor at Purdue University. Thank you all for joining us and to share this very interesting topic and project. Natasha will get us started.
Thanks, Kathy. A little overview on where our project is. We're in Colorado, which is in the western half of the United States, right at the heart, the Rocky Mountains. So an overview on the Colorado Department of Transportation. We have 8,600 bridges in Colorado. 3,500 of these are owned and maintained by CDOT. The rest are owned by local agencies or toll entities. Now, the way that CDOT is organized, we have 5 different engineering regions, kind of one for each corner of the state, and then one in our metro area. And that's where headquarters sits. That's where our staff bridge department sits. And our staff bridge department is centralized. So we have a centralized office of bridge designers who support the regions in project delivery. So project delivery is decentralized. And the project that we're going to be talking about today is actually in Region 3. It's highlighted by that yellow star. One of the areas kind of close to that is famous Lake City, Colorado. I got a picture here from a camping trip that I took last summer. So you can see it's a beautiful area of the state in our warmer months anyhow. Now, this specific project is located at Blue Mesa Reservoir, and it's in a very remote area of the state. So this is 3.5 to 4 hours from the metro areas of Colorado Springs or Denver. And you can see, and Keely will get into this a little bit more, but when we had to close these bridges, the detour around these structures was significant and really impacted the rural communities down there. So really high profile, important project. Getting into our next slide and kind of the project delivery. So CDOT was on an emergency timeline to get these contracts stood up. So we went through the emergency contracting process and used CMGC delivery process. So we were lucky to get Michael Baker International on as our designer and Hewitt as our general contractor. And there were a lot of benefits to this method. You know, we were able to get a better handle on material availability and pricing, risk identification throughout the project, schedule, constructability feedback from the contractor to our designers as we were working through things, plans and specs quality review, as we're working through the process, and then being able to phase the work and get construction started as our designers were continuing to work. So with that, Keely, I'm going to hand it over to you to hop into the details.
Thanks, Natasha. So now that we know a little more about where our location is, I'll tell you a little bit about these bridges in particular. So we were primarily looking at two bridges, KO7A and KO7B, also known as the Lake Fork Bridge and the Middle Bridge along this route, US 50. Both bridges were built in 1963. Before this project, they were in fair condition. Their main spans for both structures were continuous. Well, the plate girders, two girder system over 3 spans, and then with approach spans. So A had 6 spans total, and Bridge B had 10 spans. They carry 2 lanes, 1 in each direction on both structures over the Blue Mesa Reservoir, which you'll see throughout the project. So why were we out here? The main reason that CDOT was looking at these structures was because of the memo that FHWA issued in 2021 in response to several other high-profile bridge closures related to this type of steel. So Hernando de Soto, Sherman Mitten. After that, they issued a memo requiring each state to identify which bridges had this material on it, to test that material and any welds that were in it, and then to mitigate or repair any defects that they found in the T1 steel welds on these structures in non-redundant steel tension members or fracture critical members at the time. Colorado had identified the 2 Blue Mesa bridges as their only 2 bridges having this T1 steel with welds in Colorado, with these non-redundant steel tension members. So they were out there looking at identifying where welds were located in April of 2024, and that was the start of this project. So what is T1 steel? What do we mean when we say that? On this project, it is a high-strength steel that was developed in the 1950s. It was used heavily throughout the 1950s through the 80s. On this particular project, our ASTM designation for this structure was A514 for the pieces that were T1 steel. There were actually other types of steel on the bridge as well, but the ones we were primarily concerned about was this T1 steel. And the reason we were concerned about it is the fracture potential of those welded joints. So T1 is a marketing name that was used by US Steel during this time frame for this high strength steel, and it has known weldability issues that primarily are due with hydrogen cracking that cause concern for these structures. So an overview of the timeline for this project. I'll get into some of the details on the other slides, but as an overview, this is the general start of the project was in April when they identified the crack. The bridge was reopened to traffic on July 3rd after some critical repairs, and then the construction finished up in November 24. I'll get into some details on each of these phases of the project. So initially in April, CDOT and their consultant for inspection were out identifying what welds were actually in T1 or in the T1 steel material. There was some discrepancies between the as-built and the shop drawings and what was actually observed in the field. So they were trying to identify where these locations were. The inspector from one of the consultants was out on the bridge and observed this crack as shown in this picture right here. So it circled in red. This is what they saw before as they were out there identifying the welds adjacent to this weld. When they removed some of the paint, they saw that this was in fact in the weld material. This was only on one girder initially on the 11th. They closed traffic on the one side of the bridge and detoured it to the other side of the bridge, continued their visual inspection to find the other weld locations, and during that on April 18th observed a crack in the adjacent girder, so with a 2 girder system in both girders in the same cantilevered section here in the middle between the pin and hangers. At that point, the bridge was closed to traffic, and they started looking for CMGC designer and contractor. And by April 20th, Michael Baker, Kiewit, as well as Benish and BDI to perform some of the testing and inspection were all under contract and began working with CDOT to reopen the structure. On April 22nd, we began the UT of these butt welds in earnest. So after the initiation of the project, testing really began. This particular site posed a lot of problems to even identify what other cracks may be present in this bridge before we could get it reopened and safely to the public. One of the biggest constraints we have is because the T1 steel issue that they were concerned about is a fracture problem, any cracking would have been sudden, and they did not want to have any kind of safety issue on the bridge. So establishing what equipment and how much equipment could be on the bridge was really important and did slow down the process because we had to find equipment that was under the weight restrictions we had on the bridge, which was basically an inspection vehicle that had crossed the bridge the day it was closed. So we used finite element modeling to identify what the stresses were in the bridge from that vehicle crossing, and then kept all of our inspection equipment underneath those stresses at any given point. So access became a really big issue. Additionally, April in this mountainous region is still part of the winter season. We're still getting quite a bit of wind and weather, and that did restrict the amount of time that our inspectors could be out removing paint or identifying butt weld indications. So it did take us until May 24th to get complete inspection of all the butt welds on Bridge B. Throughout that month, we were actually designing individual repairs for any indications we found and doing additional testing. As we started to get to the end of this month, paint removal at a couple of these butt weld locations revealed some individual fillet welds cracking between the flange and the web. And that kind of started some new investigation and changed some of our design ultimately. The critical bridge repair plans to fix only surface breaking cracks so that we could reopen to some limited traffic were completed roughly 1 week after the testing was complete and fabrication started and construction on those critical elements. Next, we moved into design of the permanent repair and construction of those critical repairs. So at this point, as I stated, we started seeing these little transverse cracks in the fillet. This is the web here, and this is the flange. So we started seeing the same hydrogen cracking along transverse cracks along that fillet weld. As we removed more and more paint, it became clear that this was prevalent. So you can see these black lines in this picture. All of those are transverse cracks in the fillet weld. And that really changed how we were going about the repair and whether a global or local solution was necessary. By July, the critical repairs were, which I'll talk a little bit more about in the next few slides, were installed, and the bridge was reopened to local traffic by the July 4th holiday. Throughout all of this time, we were also looking at what that permanent solution could be. After they opened the bridge to limited traffic, they started working on the permanent repairs. Those plans were already in the works, and they had gotten an early package to fabricate the steel plates. So the RFC package was issued on August 1st, and they began permanent repair even before that with some of the early packages that they could complete. All of this was completed by November 12th before the snowplows needed to be on the bridges for the winter season. This gives you a good idea of the actual scope of the problem. We use this, it's a roll plot of the two elevation of the two girders. So the flanges are on top here. This is showing you mostly the webs with all the stiffeners. Every day, we basically track the progress of the UT. And one of the reasons this took so long is you can really see on Bridge B, we were finding that most of the welds had some kind of indication within the T1 steel. So we only tested areas within the tension zone for the structure, and then only welds that had that T1 steel. The red basically indicated a class A indication. Yellow was B and C, and then no indications or a class D indication was labeled green here. And the purple boxes on this represented fillet weld indications that we were seeing in that transverse. Any red or yellow was considered a rejectable weld defect and needed to be mitigated with the permanent repair. This just gives you another view, kind of more 3D in our BIM model, where all the indications were located. You can see that they're throughout the bridge, not only the hanging span here between these two pin and hangers, but also in the other continuous spans along the structures. There were some in the top flange tension welds, many in the web welds, and then also in the flanges. The red here indicates the surface breaking cracks. So you can see by the numbers in this table, we had a total of 118 splices that we considered to be in tension that were welded, and we tested all of those on bridge B. And in those welds, we found 289 individual indications and 5 surface breaking cracks. So the surface breaking cracks, everyone, a collaboration between FHWA, CDOT, and the designers decided that to reopen the bridge to traffic, we needed to address all the surface breaking cracks before it could be reopened. The other cracks, because hydrogen cracking happened during shortly after fabrication, it was determined that these indications had been there and that from the beginning of the bridge, and that it could safely handle local traffic once these surface breaking indications were addressed. So the critical repairs were addressing these 2 cracks on the 2 girders in the cantilevered span and the hanging between the 2 pin and hangers. And they were designed to fabricate, install, and reopen the structure as quickly as possible. So they were really designed for speed. The 2 points that I have highlighted here are the 2 places that we had cracks. To provide a little bit more comfort with reopening the structure, we did the adjacent girders at the same locations. These locations were adjacent to the field splices in the girder, and so that needed to be accounted for in the design. Because we had weight restrictions on the bridge, these plates also needed to be under a 9,000 pound limit, so that the crane could move the plate out onto the bridge and then suspend it underneath. Because we were so weight restricted by the limits of the bridge, we also went with an underslung design so that the crane could hold the plate in place while they were installing it without any additional equipment needed. So here are some pictures of what those plates look like. We worked with the contractor to integrate our hold points and to work with the existing field splice to switch out the bolts. It again was only to address the surface indications, and this was the main goal, to get the bridge open to local traffic by July 4th. We used 50 KSI material on this section because it was readily available to the fabricator. They could get it in April and start fabricating those plates right away. We were also limited with how wide we could go by what bolts we could get, not only their grade, but also the length of bolt we could reasonably procure during this time frame. And all of this had to be detailed in close coordination and collaboration with the contractor in order to consider those load limitations on the bridge. Again, as I said, at this point is when we started finding a lot of this web flange fillet weld cracking. And Francisco will talk more about the solution, but that really changed the direction of where our permanent repairs were going. The substructures were load limited. There were some load reasons that we couldn't add additional load to the substructure units as well. So we were trying initially to keep these local to minimize any increase in loading on the structure. With that 50 KSI material, it's so thick to get it to basically have the same capacity as the 100 KSI steel. that we were running into some problems. But as we started seeing these fillet welds cracks as well, we kind of switched directions that really moved the goalpost, and we had to go in a different direction towards more global plating solutions. At this point, however, we did catch a lucky break, and AVCO was able to find 100 KSI material. So they were able to basically do some special rollings or add to their rollings that they were doing for other industries to get us 100 KSI material in 3/4 inch and 1 inch plies. So this was really a game changer and allowed us to consider global solutions that would also address these fillet weld cracks without having to identify all the locations, which was very time consuming because of the paint and the length of this bridge, and allowed us to minimize any impact to the substructures. It also allowed us to minimize the visual impact because this was a historically eligible bridge, and that was important to the community, that you couldn't see these repairs from the shores, which it's much easier to do with these smaller plates. So here's a general view of the permanent repairs that were developed throughout this project. So we had top flange plating because we did not want to open up the entire top flange section and have a large portion of open deck during the permanent construction that would have to close the bridge. We actually went with local repairs in the top flange sections and tested the fillet weld for the entire length in order to make sure that we didn't have any of those flange to fillet or the fillet weld cracking. These were 50 KSI so that they could start working on them immediately, and then required a small deck removal in order to get those bolts in. We had a web butt weld repair plate. So this basically addressed any indications that were in that full height weld between sections. We had the web to fillet weld crack arrest plate, which Francisco will get into some details, and then some continuous bottom flange plating in all the tension areas in the 3 main spans. Additionally, we had to do some other work in order to get more construction loads out on the bridge. We added a couple cross frames to address some lateral torsional buckling issues that kept construction equipment off the bridge, and we had some new knee braces in order to accommodate some of our plates. With that, I have a couple quick construction photos to show you, just to give you a sense of the scale of some of these repairs. So some of them did end up being larger in the top flange, where we did have a lot of fillet weld cracking. So you can see a larger section. This is one of our local repairs. And as I said, those were 50 KSI and were designed to try to minimize our deck removal and the duration of the impact to traffic. These are the bottom flange repairs, and it consisted of these 5 plates, basically. So with bottom plate, 2 interior plates, and then these web crack arrest plates. This was not designed to be a redundant section or to have redundancy in the end, because it was really plates to replace any cracked section should a crack occur in the future. We sourced the grade 100 plates, as I said, but we were all bolted connections, so we didn't have any weldability issues in this modern steel. And then this allowed us to minimize the dead load impacts on the structure. And this is a good comparison of what the difference between that material really meant to this bridge. This is the critical repairs that were done with 50 KSI steel. And then on this side, we have the repairs that were done with the permanent with the 100 KSI steel. So we were able to remove quite a bit of weight from the structure. And with that, I will turn it over to Francisco to get into the details of the web crack arrest plate.
So, well, thank you, Keeling. And before I continue, I was going to talk about the development of one of the repairs, but I had to kind of present a little bit of the characters in the gaming here. When we were working this at Michael Baker, we reached out to Professor Connor at the S. Bright Center. Back then, I was also working for Baker. Now I'm working at Purdue University. The S. Bright Center is the Steel Bridge Research, Inspection, Training, and Engineering Center, Purdue University, which is a center that is funded through DOT, and basically there's like some DOTs that are members. There's 24 of them, plus Federal Highway Administration. And the objective of this center is to provide resources and to provide expertise and get involved into this, especially get involved into some of these problems that are a little bit more complex. Also, in this center right now, we are currently developing the bridge engineering program at Purdue University. Also, we're planning on developing a bridge engineering education center, a facility within the S-Bright Current facility that you see there on that image. Those are things that are coming. But anyway, going back to the main, as Keely brought up, the issue stems from the embrittlement issues that occur in T1 steel. And we had one of the problems that we encountered, it was that in the web to flange fillet welds, we have defect indications throughout the length of the girders. So the extent of these indications made traditional repairs kind of unfeasible, and this added to the concerns that this was an NSTM member, or a non-redundant steel tension member, which used to be known as fracture critical member. The concern is basically that if you were to get a full fracture in the member, a full section fracture, that might lead to collapse of the structure. And this led to basically the development of a repair that was a continuous retrofit that had to be effective regardless of the location of the actual location of the crack or any hypothetical location. So when we encounter this kind of wet to flange weld issues, the typical approaches are either based on coring methods or the installation of dog bone details. So you would typically use a coring method as shown in this picture in here. When you already have detected a crack extending from these wet to flange indications, and then you will core out the tip. By that, you reduce the stress intensity that occurs at the crack tip, and therefore you now have a blunt crack that don't grow. If you don't know where the location of the crack is, you typically do a dog bone detail that is basically two coring holes joined by a slit with the intention of intersecting the crack as it propagates. So as we had so many details, these were basically unfeasible. If we were to put dog bone details throughout the length of we would have had to put dog bone details basically throughout the length of the girder, and that would have basically made the bottom flange separate, or the tension flanges to be completely separated from the web. And the other type of approach to this type of problem is to install a full web splice. Basically, you sandwich the entire web, and then you additionally would have to provide some kind of connection between the web, then the web splice, and the remaining components of the flange. So as you can see, this would have been quite a bit of additional self-weight to the structure. And in terms of feed up with other repairs that were already in the structure, it would have been quite a nightmare, basically. So the common solutions would have been useful in this case. And additionally, we have quite a bit of inspection uncertainty. Throughout this project, we were getting, basically, as we were conducting more and more evaluation of these wells, we were finding more and more indications. And this was kind of also showing that it was probable that we would have had more indications or even some cracks in locations that we haven't already identified. So what do we do regarding this? How do we develop a retrofit for a crack that we know it might be there, but it might be anywhere? So to develop the retrofit, we basically developed a concept that was based on understanding how stress fields change around bolt holes and how cracks respond to them. So this, if you were to, in general, when we have seen cracks growing, particularly in bottom flanges in riveted members, it's pretty common for a crack to emanate from where you have a rivet hole and then finds its way to an adjacent hole. The reason is that, as it's shown in here, the stress field around a bolt hole, or in fact any hole, if we look at the hole in the direction of stress in a plane perpendicular to that direction, you will find that you have these hot spots of stresses on the sides of the hole, and you have in front of the hole, you have sort of like a stress vacuum. So what happens is basically that we know that the stress intensity here is about 3 times the far field stress. And then we also know that if we were to have a crack in an infinite plate, that it would be coincident with that plane that is perpendicular to the direction of stress but aligned with the center of the hole. If that initial defect was in that plane, it will grow towards the hole. We also know that the far field stress, the lowest stress that defect we'll find along that, any location out on that plane, it will be basically the sigma x0, the far field stress, and that the product between the opening stress and the direction of propagation, if we take the modulus of the cross product, it will be 1. So that was sort of like the development for the concept for the development of our repair, was to develop a field of holes in a way that the stress conditions in the locations where the crack might propagate correspond to those ones that I describing here, or are at least a little bit better. So just to kind of like to further emphasize this, if we look at this plot where we have a set of holes that are going to be used as the crack propagation repair, as we can see, these red areas are locations in which the stresses have increased, the opening stresses have increased, and the blue areas is where we have that vacuum. So basically the concept is that a crack originating anywhere along this location, that would be the corresponding to the web to flange location, any crack growing along there will either find its way to the hole, or if it misses this one, will find its way to the next one. So that's where the development comes from. In theory, we developed this, so in theory, we would only need 2 rows, but we added a 3rd row of bolts for redundancy. And then we developed a series of spacing that met the cross product criteria that I described before. So once we had this preliminary concept, then we contacted Dr. Rob Connor and Dr. Korkmaz at Purdue University with the S-Brain Center, and then they conducted some validation using Abacus, the finite element software. Within Abacus, they use XFM, Extended Finite Element Method, which is basically a method that overlays on top of your finite element mesh and enrichment functions that allow you to model the crack discontinuity and then also the stresses at the crack tip a little bit better. In addition to that, it has a crack propagation scheme so that if you meet a certain criteria, the crack propagates. So we sent a series of patterns, of bolt patterns, to Dr. Korkmaz and Dr. Connor at Purdue University, and they provided some validation using the extended finite element method. And basically what we found out is that the majority of the cracks tended to end in the first row of bolts, with only some extending into the second one and none of them going into the third one. And during this evaluation, they used different crack propagation criteria with different energy release rates and a different mode 1 to mode 2 propagation ratios as well. So basically try to consider all fracture propagation conditions possible. And then finally, once we have the bolt pattern that we wanted to implement, the last thing is to provide a series of modifications so that this retrofit is compatible with the other retrofits that were already in the structure. So as I said before, basically the final retrofit for this is 3 bolt rows with a defined minimum and maximum spacing limit, and then web reinforcement plates placed on each side in order to maintain capacity of the web if a crack was to emanate from the web to flange and propagate into the web. As the retrofit also require additional compatibility with other additional retrofits, particularly when we have already like a core web crack location, maybe we have to interrupt the spacing through there, try to implement a web bone, dog bone detail, or also near existing flange splice retrofits where we have like pad welds in the web itself. And in those cases, we basically came out with where we couldn't maintain the spacing of that bolt pattern, we came in with an additional dog bone crack arrest detail over there. Basically, this adjustment allowed us to provide a consistent crack arrest performance across the structure, and we had basically through the entire section of the girder that has the web to flange weld subjected to tension, we have provided a retrofit that will be able to prevent any crack propagation from a web to flange weldment into the web. I think I'm done presenting I'm gonna turn it back to Keeling.
Thanks, Francisco. Next, I just had some kind of wrap up information and some lessons learned from this particular project. So this was just to give you, again, a sense of the scale of this project. We had over 118 splices that were tested on Bridge B. As I said, there were over 289 indications found between the 2 structures. The length, the depth of these girders, and the design at the time in the 60s was to change the plate sizes as often as you could to save material. And so there were quite a bit of these repairs that were needed. And so you can see that in the 35,000 square feet of primer that was put onto the bridge, 410 tons of additional steel between all the plating and 51,504 bolts, which equated to over 57 tons of just bolts on the structure. I also wanted to take a minute to thank all of our partners. There were a lot of people, as you could see with the length of this detour. It was important to get resources out on the structure, not only for design, but for construction, inspection, CM management. So there were a lot of different companies and people involved. Special thanks, of course, to CDOT Region 3 and Staff Bridge, as well as Gunnison County. There were some local detour routes, but that were actually improved in order to get small traffic through the area and keep these communities connected. There were people taking kids to school across on boats. So there were a lot of people that really came together and supported this, as well as our inspection and testing through Benish and Bridge Diagnostics. Of course, Rob Connor and the Esbright Center, as Francisco noted. FHWA, the coating specialists and paint removers were very important on this particular job. There was high chromium in the paint, and so it did require specialized equipment to take the paint off the structure, as well as our construction manager, Stantec, and all of their subs that they had out on the structure all summer of 2024. And then, of course, special recognition to AVCO for finding that material that really made this solution possible. A few of the lessons learned, really the story of Blue Mesa is a story of collaboration. Everyone wanted to get this bridge open, talked and collaborated, come up with solutions. And that really allowed us to come up with a solution that worked best for this bridge and got it open quickly. There were also some unique challenges on this structure compared to other T1 steel structures that have been repaired that can be taken forward, and why the Plinko plate, the cracked rest plate, was really necessary on this bridge. One of the big reasons is that this was a girder bridge. So we are working with bending, that the tension is changing throughout the web and throughout the length of the structure. Whereas a lot of the T1 steel that had to be repaired was in truss members, so tension only members. So it offered some unique challenges that we can take forward into other projects. On Bridge A, our lessons learned from trying to remove the paint from the extent of the weld defects on Bridge. CDOT actually elected to forego testing on Bridge A, and we just went with a solution where we plated every single weld in tension on Bridge A, and that allowed us to get everything completed by the end of 2024 by foregoing that testing. And then, of course, with any CMGC, the importance of communication, both internally and externally. So with the contractor, the client, the designer, inspectors, but also with the community, so that we could have their buy-in to the solution. And then that improved constructability and the benefits of CMGC on our emergency project really shown on this particular project. Finding the right materials and minimizing rework in our design by finding out what the contractor could actually get, and then working backwards to a solution that worked for the structure. With that, we can take any questions.
So we're going to turn it back to Paul Lyles, Kathy Kroll, and Bijan to moderate the question and answer period.
Okay, so the first question is, if the bridge was constructed in 1963, then what ASTM or actual specification covered 100 KSI steel?
I believe it was everything on this bridge was ASTM 514 that was T1 steel. There was also a 440 steel on the structure, but all of this was basically before the fracture control plan welding requirements of 1978. So that was really the main issue. It wasn't necessarily the material, it was the welding procedure, and how we do that now was not in place at that time.
Good answer, thank you. The second question is, what was the design load versus the design capacity of the weld?
So it was designed basically to account for plate crack of the element it was bridging. So that's how we approached that design. So, net area and all those kind of things, and tried to replace that with our plates.
I think the question is regarding the design capacity of the well versus the load. We don't believe that there were any sort of like design issues in the original design of the structure, that any of the wells were undersized or such. The issues were regarding, as we were saying, related to hydrogen cracking and brittlement on the well. And those happen a little bit after, in this type of steel, T1 steel is issue. It's basically an embrittlement that takes place after the well metal has been laid out and it's delayed. It needs to, basically the base metal needs to cool down until before the cracking develops. So if the question is regarding if I don't know, we don't know off the top of our heads the capacity of each one of the wells that had to be addressed, because there was a lot of them, but we don't believe there was an issue basically with any sort of design issues with the original design issues with the well.
Yeah, you can provide more detailed answer to the questions later on. So thank you. The next question is, what fatigue category was the well?
Well, if I'm not mistaken, a bad splice well in a tension flange, that should be category D, I think. But it's up to the geometry. There were bad splice wells and, web fillet wells that are like flange to wells. So we're talking about, like, in general, I think there will be category C's, category B wells. So they were not like weldments that you will find at, to say category F. They were not like they were not E or E prime wells, basically.
Okay, moving on to the next question. What type of a steel is this? High performance steel? They're asking if it's a high performance steel that you used.
So HTS steel is a steel that is you may use it. Is meant to be used particularly for tension members where you think you might want some additional fracture toughness. So high performance steel has a better fracture toughness, which basically means that if you have a fracture indication, it will be less susceptible to developing a fracture or in that indication growing. So it has higher fracture toughness. They also have better weldability, the steel. So that's why they are geared towards their use, particularly in tension members, especially in fracture, what it used to be called fracture critical applications or NSTM applications.
Okay, thank you. Moving on to the next question. How long do you anticipate the repairs have added to the life cycle of this bridge?
It's an interesting question. It's hard to predict, of course, what else might go wrong on this bridge, and assuming, all other maintenance and those kind of things. This bridge was actually funded, the repairs were funded by a particular semi-agency, so it's called Bridge and Tunnel Enterprise within Colorado. And so because of their requirements, we're trying to aim for a 30-year life expectancy for these repairs. There's some additional like painting and stuff that needs to go into that, of course, and it's hard to predict, but that was what we were going for.
Question 6. Could you please explain the cause of the cracking and how this issue can be prevented in the future? And will other structures be affected?
Okay, so what can you do to prevent it? First, regarding the origin of the crack. Hydrogen embrittlement is basically a phenomenon that occurs during weld fabrication. You need to have a steel that is relatively susceptible to it, like T1 steel. And what happens is when you fabricate the well, there is inside of base metal, you get basically an absorption of hydrogen into the area, and that generates embrittlement. It makes the material brittle around the heat effective zone. And then when it cools, that generates some micro cracking that eventually develops into a large crack. That's the origin of the crack. What can you do to prevent it? Current fabrication, if you follow the bridge welding code, you will not have these issues. So the fabrication process to prevent hydrogen embrittlement, it's already well defined. Now, for other structures that are out there, as Kelly mentioned, FHWA sent out a notification, I forgot when it was probably shortly after the Hernando de Soto
Yeah, it was
issue,
2021.
requesting DOTs to inspect basically with a list of bridges that might have T1 steel, to basically go in, inspect them, and assess if they have any sort of indication. So that's the process that we are following. We're looking at the inspecting, doing MDT on the ones that we know that use the material and are susceptible to this type of cracking. And then for newer structures, we already have fabrication processes that handle it well.
Great. Another good question. Question number 7. Was the cause of the cracking determined? And if so, how?
It was pretty much agreed by all the different parties that this was likely the cause of the cracking, but we did take cores of several of the indications that were large and had them tested. Basically, you know, looking at it in section, you can tell if that was what it, you know, in a thin section, you can tell what it was, and those did come back that this was the hydrogen cracking was the cause.
Thank you. We are going to question number 8. Can you discuss the inspection plan and what non-destructive evaluation NDE method were used? After the cracks were found, what was the plan of action?
Yes, the inspection plan, initially they were looking and identifying those welds with the intent to do UT on those welds. Once the crack was identified, we basically expedited that initial plan. We removed the paint. Initially, we did a few testing to see if there was any other kind of testing that could identify the cracks through the paint in sections that we knew where there was a crack. However, we found that you could not test through any of this paint. So on all the butt welds, we removed the paint for about a foot on either side of that weld, and then did initially single phase UT weld on all those butt welds. Once we identified the fillet weld cracks, we actually did some phased array, and that allowed us to identify that those cracks were not only in the fillet weld themselves, but had actually extended into the flange in several locations, which is what made that so concerning, I guess, or that we really wanted to address those fillet weld cracks as well. They did all that work from snoopers mostly, which was difficult in some of these locations because it's a fairly deep girder. So finding equipment, there were only 2 or 3 pieces of equipment nationwide that could actually get up underneath and look at the inside weld on the top flange.
Bijan, let's go ahead and jump over to Paul.
Okay. Now, we do have a bunch of questions, and we'll try and get into them. The first one I have, can you give us indication of the ADT on the bridge and maybe percent trucks? Would you have that information?
Yeah, it is a rural route. It's not a huge amount, but there is truck traffic. This is the only route between Gunnison and Montrose, Colorado. There's a national park very close to that, the Black Canyon of the Gunnison. So it gets a lot of traffic during the summer. This is it's mostly recreational and local stuff.
That's fine. That's good. Then the question was, are these bridges hybrid where you use the webs of a different grade than the flanges, or is it all 100 KSI steel?
So the sections, they were not hybrid sections. It was different sections were being welded in, but generally the web, flange, and top flange were all the same steel. So there were a couple different steels that were used depending on where you were in the structure, but they were, the section itself was not mixed.
All right, and then in the early 60s, these weren't composite bridges, were they? Sheer connectors on the top?
They were actually composite in the, if I'm remembering correct, I'll have to check and get back to you on that one. I'm pretty sure they were composite in the positive region, is what I'm remembering.
All right, that's fine. Okay, now, here's the question that, in the present day, would Colorado DOT consider a new bridge to be a 2-girder bridge, non-redundant load path, or would you really put a bunch of girders in?
Yeah, it sounds like the question is asking if we would design a non-redundant steel tension member bridge again, and I would say no, probably not.
That's Georgia. You can't widen them very well either. That's another problem with them. Do you have any idea what the reason was for all the defects? The question was it structure, or was it maybe defective material?
There did seem to be some indication of problems with the welding. There were some back gouges and areas of non-fusion and that kind of thing. They did have a repair weld that was done later in that same steel that didn't have any indications, but all the welds on all the welds we tested, except for that one repair weld, did have some kind of indication in them.
Okay. Well, the question was on were the welds inspected prior to construction? And if so, do you know anything about the inspection method? They used to use X-rays back then. I don't know what they did in this case.
Yeah,
okay.
There wasn't any record in what we had during design, at least.
Okay. Now, you indicated you'd have 30 years more life out of the bridge. Is that what you were looking at?
That's what we were trying for, yes.
And then you'd maybe replace it after that? Question that they had.
Yeah, I think hopefully there was talk of like, what about the replacement options? That just wasn't considered because of the time to fabricate steel at the time. They were at least 18 months out to fabricate steel beams of similar 4 or 5 girder system, and they did not want it to be closed that long.
Okay. Could you say anything about the classification of the NDT indications? You had the picture with all the different colors on it. The question was, is this based on engineering judgment, or is there some standard to group those into those categories?
There is a standard. The UT test is a little bit subjective. It's based on like a reading of the response you're getting in that testing. But we basically had the NDT had the certification, I think actually from Purdue, right, Francisco, to do that UT, and then we actually had an independent tester that QC 30 or 10% of the welds.
There were more than one comparison. Basically, there were several people involved with the NDT, with the ultrasonic testing and with the calibration and so forth. But yeah, pretty much. There was like a couple of. There were 2 firms that did, at least 2 firms that did measurements on the bridge itself, and there were Curtis himself maybe I forgot who was involved, but there was other people that were involved, basically making sure that the calibration was done correctly and so forth. Yeah.
But there is a standard for like how to separate them out.
Is basically you get a change in your measurement of decibels from a wave that you send, and based on the change and where the location of the defect is within the thickness of the component, you kind of like assess whether it's a rejectable indication or a non-rejectable indication. That's kind of how it goes.
Let's get one more question here. What grade and size were the bolts? Are they conventional A325 or a 7/8 inch, 1 inch diameter, or maybe were they higher strength? Were they 490, A490? You may have mixed them up.
Mostly 325. But there were some 490 depending on where you are on the bridge. It really depended on the grip length that we could get.
Got one more question. Was it they looked like multiple plates on the bottom and maybe stacked plates? Could you use one plate, or what'd you do for stacking them? Or were they filler plates, or what'd you do there?
That was primarily to get that 100 KSI steel. We had to go with, on the permanent repairs, we had to go with plies of 3/4 or 1 inch. So we had to, combine them in whatever way. On the 50 KSI steel, we did some plies on that as well. But that was mostly to keep that weight for construction under 900 pounds or 9,000 pounds, so that we could bring that plate onto the bridge without causing more stress than we wanted to.
Okay.
All right. Okay, Paul. Thanks to our speakers, and thanks to Bijan, Paul, to moderate the question and answer period. It was very informative. Again, to our audiences, deadline to submit a 1-page abstract for the 2026 World Bridge Engineering Conference is March 20. Please take a note. So it's going to be open until tomorrow midnight to accept basically the abstract. So until we hope to see you in the conference, and until our next monthly webinar, thank you.